first with the theoretical part. Then we will continue the problems of chapter 3. So hopefully today we will finish with chapter 3. Okay. So last time we have introduced the Rankine cycle, which consists on if you want an example, is a steam power plant consisting of 4 elements, which are the boiler, the turbine, the condenser, and the pump. And this cycle will be repeated, so it's a closed cycle, and it's the same fluid that is circulating through the system. This is why we call it a closed cycle. Okay. Now, as we can see here, in the Rankine cycle, we have 4 steps. So first, at state 1, let's say here, in general, we have the steam in state of saturated liquid. So as you can see here, it's represented by point 1. Point 1 just 1 minute because some people are still entering the meeting. So here we can start first. This is the inlet of the pump. It's at the saturated liquid phase. Then here we have, in the liquid zone, we have the pumping effect. And we said that it's not advised to have a vapor part in the pump because it will harm the equipment. Then the pressure will be increased in the pump, and the steam in the liquid state will enter the boiler. Okay. In the boiler, we have heating at constant pressure. So first, since it's a constant pressure, we will follow isobars on the diagram TS. So first, the temperature will increase until reaching the saturated liquid state. Then we continue at the same pressure at constant temperature. Here we have the phase change. And after that, when we reach the saturated vapor state, we will continue into a superheated zone until reaching point 3. And the objective mainly of the superheating is, one, to increase the efficiency, because like when you do this, you increase the area here, which is the net work. So it's good to have superheating. And the second advantage is that you at the exit here of your turbine, because you are in the turbine, you have isentropic expansion. So at constant entropy. Okay, so you move along constant S. Then as you superheat, you can reach a point which is close to the saturated vapor. So you can lower the moisture content here. And in the final phase, you go through the condenser where heat is rejected in order to repeat your cycle. Okay, now okay, so now if we continue, we did last time the analysis of how to calculate the efficiency of a Rankine cycle. Now we will see some strategies to increase the efficiency of this cycle. To start with, okay, we can lower the condenser pressure or lower the temperature at the condenser also. So here, as you can see, at this level, this is a comparison between 2 cycles. This is the first one, and this is the second one. In the second one, we decrease the pressure at the condenser level. So as you can see, due to this effect, the area here will increase. So the network will increase, because you know that the network represents the area limited by the curve. So here, since you have a higher area when you decrease the pressure, then you will have a higher work in a network, higher network. So it's a better efficiency. But what is the disadvantage? Who will tell me? What is the disadvantage?
Yes. The water content is higher because the quality is lower.
Very good. So here for the turbine, it's not good because the quality is lower. So it's true that we have an advantage of increasing the efficiency, but also our turbine, to keep our turbine and avoid the
Use.
corrosion, then we should pay attention to not lower a lot the pressure at the condenser level. Okay? Now, another strategy for efficiency improvement is to do superheating, as we have seen before. Okay, so as you can see here, for example, if I increase the superheat, I can first I will increase the work. The net work will be increased because the area under the curve will be increased. So the area limited by my cycle will be higher. So it's a higher work output. But at the same time, plus this is the second advantage is that I can reduce the moisture content at the exit of the turbine. So it's very good. Doing superheating is very good. But what can be the limit for superheating? Why I cannot reach a very high temperature?
Because you will have fusion of the blades and the turbine. You know, the blades
Very
might
good,
be.
because it's harmful, very good. It's harmful for the turbine. This is why, in case I want to reach very high temperature, I should do extra design in order to have material properties that can sustain such temperatures. In general, the high steam temperature allowed in turbine inlet is about 620 degrees, so I cannot go beyond. Okay.
What materials are usually used for turbines?
You have alloys, and it's not one material. You have combination of several materials that have very good properties in sustaining high temperature. Okay, so you can use different types of alloys, and the combination in general is studied experimentally to come up with an optimal configuration. Now, so as we said, we have a certain limit for the maximum temperature. Since we have a certain limit that we could not exceed, we have thought about a new strategy to increase the efficiency while not reaching a very high temperature. The idea is to do several reheat steps. Okay, so what we mean by this is the following. So instead of putting one turbine in the cycle, we can put two turbines. Okay, so in this case, just before the idea of reheat, we have also another strategy. If we have the same, if we have to not exceed this temperature, we can think about increasing the pressure in the boiler. Okay, so as you can see here, if I increase the pressure at the boiler level, I can increase the net work, but at the same time, what is the disadvantage? Because look, if I follow this line, this pressure line, which is a higher pressure, higher constant pressure line, the problem is that now, at the exit of the turbine, I have a higher humidity level. So it's the same issue here, that if because here I increase the proportion of water droplets at the exit of the turbine, so it's not a very good strategy. This is why we thought about doing reheat. Let us see what is the reheat. The idea here is, in order to first not exceed the maximum temperature, so this is the first constraint, I should not exceed a certain temperature, and at the same time, I don't want to have at the exit of the turbine here, I want to have a quality close to 1, to not have water droplets, a lot of water droplets at the exit of the turbine. So to do this, the idea of doing reheat, what do we mean by this? So first, we have a high pressure turbine, as you can see here. So first I do the first reheat, the first superheating, okay? Then I exit my turbine, but instead of going directly doing one expansion in one turbine, okay, I divide the expansion into stages, Okay, so I do a first expansion in the first turbine, and I stop, for example, here at a certain stage. I remain into the zone which is in the vapor zone. Okay, then I enter a second turbine that is at lower pressure. So now I do a reheat of my, so I do reheat in my boiler. So before entering the turbine of the low pressure turbine, as you can see here, I should reheat my steam. Okay, I reheat my steam until the maximum temperature. So I benefit here from extra, so I can have extra heating and without exceeding the maximum temperature. Then after this, I can pass by again a new turbine, which is at a lower pressure. And then I can do my expansion in the turbine and exit at state 6, which is a good state because the quality is close to 1. So if you want to see it here in the figure, so first in the pump from 1 to 2, it's the usual pumping stage. So this is the pumping stage. Then I enter the boiler. At the boiler level, I have the heating, the first heating phase. So I will heat. This is the first heating phase along the constant pressure of the boiler, and it's a high pressure. So here we have the, I heat to a very high temperature 3, which corresponds to a high pressure, and then I enter the first turbine at point 3. Okay, in the turbine I do a first expansion until point 4. Now instead of doing directly the total expansion, I take my steam and I enter my steam into the boiler again. So when it will enter again through the boiler, it will be heated another time, but at a different pressure. Okay, so now from 4 to 5, I am entering the boiler and doing a reheat at the lower pressure of the at the lower pressure, which is exiting the high turbine. And now once I reach the temperature needed, which is, let's say, the maximum temperature, I can now enter the low pressure turbine where I have now the second stage of expansion from 5 to 6. So as you can see, I increased, by this method, I increased the network, and at the same time, at the exit of my turbine, I have nearly a quality of 100% nearly. Okay, so this is a very good strategy that increases the efficiency of my system without without having to have corrosion of my equipment. Okay, in this case, how to calculate the efficiency? So here, since you have 2 turbines, so the net, when you calculate the net work, you should consider the work in the produced by turbine 1 plus the work produced by turbine 2. Okay, and if you remember, to calculate the work, it's related to variation in enthalpy. Okay, because if you remember, we said that the work rate is m dot times delta H. Okay, so if you want to calculate the work per unit, and if you divide by m dot, you get that the small w turbine out is equal to W turbine 1 plus W turbine 2, and for turbine 1 it's H3 minus H4, while for turbine 2 it's H5 minus H6. Okay, now concerning the total heat that is entering my system, you know that the efficiency is calculated by work produced, net work if you want. So it's the net work over the total heat that is added in, Qn, over, I will put small q because we are computed it per unit of mass flow rate. Okay, so it's equal to, the net work here is W turbine 1 plus W turbine 2. Okay, and of course for the pump, okay, if you want, it's minus W pump, because we are, for the pump we are putting work on the system, okay, over Qn. Now for Qn, It's the heat added to our steam. We have two heating stages in the boiler. Okay, so we should take into consideration Q1 plus Q2, or if you want Q1 plus Q prime, let's call it Q prime 1. What is Q prime? It's the heating in the second stage. Okay, so you can call it also Q primary and Q reheat. So first Q primary is when you heat from 2 to 3, so it's H3 minus H2, while Q reheat, which is Q prime, is the heating between 4 and 5, so it's H5 minus H4. Okay, so this is how we can compute the efficiency of such system. Any question until here? Now, sometimes, okay, in some cases, we can do more than one reheat, but it's not very practical, and it will not increase a lot the efficiency. So the most used is one reheat, okay, because it will increase a lot the efficiency and it's practical. We just need to put one additional turbine, and we can do then a second expansion, okay. Now, what is cogeneration? Okay, sometimes you know that in many power plants, and for example, the steam power plant we have considered now, we have heat that is lost. Heat is lost at which level? At which level we lose heat in the steam power plant?
At the process heater.
Condenser.
Yes, condenser. At the condenser level. Okay. So what we can do is, you know that in many applications, we have many applications that can work. For example, that needs a small amount of heat to be processed. Okay. This is why what we can do to benefit from our steam power plant to the maximum, we can, at the condenser level, we can put a process heater which will transfer the lost heat to any application that can use this heat. So in this case, we will not only, in the efficiency, when we calculate the efficiency, we will not only benefit from the output work W net, but also we can benefit from the heat that is transferred to another system. Okay, this is called cogeneration. So cogeneration consists of the production of more than one useful form of energy, such as, for example, process heat and electric power from the same energy source. Okay, so going back to our steam power plant here. Okay, your steam power plant is used to produce electricity because you will take work at the turbine level, and you will turn this work. You will use the mechanical energy in order to turn a generator, an alternator. If you remember, in the first chapter, or yes, just in the first chapter, we introduced how turbine work, and we said that we can convert the mechanical energy to electrical energy. Okay, then in this case, first, we will produce electrical energy through the use of the turbine. And second, we can use the heat that is lost at the condenser level to be used in any application that requires heat. So in this case, our efficiency will be much increased. And of course, in the ideal case, we can reach 100% efficiency. But in reality, the efficiency is always lower than 100%. For the pump, in general, the work needed for the pump is not very high. So you can reach very high efficiency, okay? Because in this case, you will benefit from the heat and from the turbine work. So nearly, in actual cases, we can reach up to 80% of efficiency, which is very good. Now, we have talked about steam power plants. And we said that we have some limitation in the steam power plants because first we don't want to reach very high temperature because of the materials used. And second, we don't want to have at the exit of the turbine water droplets, so we should take into consideration the state at the exit of the turbine. What is more efficient than steam turbine is gas turbines, which consist on the Brayton cycle. So what is a gas turbine? As we said, in the steam power plant, maximum operating temperature is nearly 650 degrees to avoid excessive fatigue. Now, in a gas turbine, combustion of gases can result in products reaching nearly 1,300 degrees. Okay, so in this case, we need to do a very careful design for the turbine blades. In this case, turbine blades are coated with a low thermal conductivity ceramic material so that the hot gases do not make direct contact with the metal surfaces. Okay, and in this case, water is cooled to avoid reaching the maximum limit of the metal. Gas turbines originally evolved from jet turbine engines in which the thrust arises from the combustion of gases, which will give the push on the blades through the adiabatic expansion of the exhaust gas. Now, how is our cycle in gas turbines? The first difference between steam turbines and gas turbines is that in steam turbines we have a closed cycle, while for gas turbines it's an open cycle. Why it's an open cycle? Because as you can see here, it's not the same fluid that will circulate throughout the cycle. You have what will take place is that for each cycle you have air is drawn from the atmosphere, okay, and it will go through the compressor. It is pumped, then it will go into the combustion chamber where it will be heated, and once heated it will go through the turbine, and then the energy of the combustion gases will be transformed into mechanical energy at the turbine level and then to electrical energy. Okay, and at the final state you have that the exhaust gases will be rejected to the atmosphere. So you are not using the same fluid in your system. It's true that you are using air always, but it's not the same air. You are drawing air from the atmosphere and then you are ejecting exhaust gases to the atmosphere. This is why we can say that it's the same pressure at the inlet and the outlet. So we can consider that if you want, instead of the condenser in the steam power plant, we have the atmosphere here that will be used as a cooling system. So it will take the exhaust gases, which are hot, and we can take from it the cooled gas again to draw the cycle. Okay. So now, if you want to represent our cycle, it's similar to what we have seen before. Okay. So you have for example here four stages. Okay, the first stage is the compression. So as you can see here, a compression from A to B. In general, the compression and in the compression phase, the temperature will increase and the pressure will increase. Then we have in the combustion chamber, you will take heat from combustion of gases at constant pressure. So you are heating in the combustion chamber at constant pressure. And then you will go into the turbine. When you go into the turbine, you will have expansion of the gases, which will lead to rotation of the blades of turbine, which will be transferred to your shaft and can produce electricity. So here you have the expansion phase. Okay, and both compression and expansion are in general adiabatic, so you don't have heat loss, but you have in the turbine work output and in the compressor work input. And finally here you can consider that between A and D, so here you have an open cycle, but it is like you have rejection of heat in this stage. Okay, so it's true that it's not the same air that is circulating, but what is taking place is that I am exiting at the atmospherical pressure and I am taking air at atmospherical pressure. So I have here rejection of heat at constant pressure. Okay, and if I want to draw the TS diagram, for the TS diagram, as we said, in the compressor and in the turbine, you have adiabatic processes. When you have adiabatic processes, you say, and we say that it's isentropic because we don't have heat loss. So we can consider that we have it at constant entropy, okay? So adiabatic isentropic processes at constant entropy for the turbine and the compressor. And in the boiler, and here we don't have condenser, but air will play the role of condenser. The atmospherical level, the atmosphere will play the role of the condenser. So you have here from B to C heating, and from D to A rejection of heat. Okay, so that's it. And in order to calculate the efficiency, it's very similar to what we have done before. So we should compute the work done by the turbine. The work done by the turbine here, okay, you can say that per unit mass, the work done is Hc minus Hd, the enthalpy at point C minus the enthalpy at point D. But also you have a second method to calculate, because here it's a gas. You can treat it as an ideal gas. And we say that in this case, you have that you can compute H by Cp times temperature. Okay, so always when you have a gas, you can say that I can replace H by Cp times T. Okay, in case, because I have here a constant pressure between B and C, it's a constant pressure process. So I can write that delta H is Cp delta T. Okay, and also for the compressor, it's the same idea because it's at a constant pressure. Sorry, I mean, no, it's not a constant pressure here because it's not between BC and AD, it's between CD and VA, okay? But for a gas, when you want to calculate the enthalpy, you can compute it as Cp times T, okay? When you have to calculate the Q, in case of constant pressure, you calculate it as Cp delta T, and in case of constant volume, you calculate it as Cv delta T, okay? But for enthalpy of a gas, you can take it as Cp times temperature, okay? And of course, another method is to, if you have tables, if you have thermodynamic tables for this gas, you can use the tables to get the enthalpies. In case not, if they give you Cp, you can calculate the enthalpy as Cp times T. Now, once you calculate the work done by the turbine, the work done by the compressor, and the heat that is given in the combustion chamber, which is given at constant pressure and is Cp delta T, you can now compute the efficiency of the cycle. The efficiency of the cycle is the work done by the turbine minus the work of the compressor over the heat provided to the system Q1. Then you can compute the value of the efficiency of the system. Okay? Now, so if you want, once you understand the concept, it's the same method for all cycles. You should look where you have, yes?
The slide, the previous slide.
Yeah.
We put that W equals Cp delta T. We said that W equals Cp delta T because it was constant. Why is it Cp delta T?
No, not. I was repeating the idea. When you have constant pressure, okay? When you have constant pressure and you want to calculate the Q, you do that Q is Cp times delta T, okay? But for the enthalpy of a gas, you can calculate the enthalpy as Cp times temperature, okay? The enthalpy of a gas is given by a specific heat of the gas times its temperature.
Okay.
So if you have constant pressure or not, so of course between C and D and between A and B, you don't have constant pressure, okay? But you are computing W as delta H. And delta H and the H for a gas can be computed as C times temperature.
Okay, but for Q لأنه it was constant pressure. I'm
هلا
بحكي
for
عن
Q always look for Q if it's a gas or if it is a liquid or if it is anything else. When you want to calculate at constant pressure, Q is Cp delta T, and if you have Q at constant volume, it's Cv delta T. Okay.
اوكي فوقت تكون constant pressure فينا نحط Q equals Cp delta T.
Yes. Okay.
Okay, thank you.
Okay. Now, another alternative of combined cycle, it would be a nice idea to combine the steam cycle and the gas turbine cycle. Why? Because you know that for the gas turbine cycle, I have exhaust gases that will exhaust my system at very high temperature. So to benefit from the energy of my exhaust gases, one idea will be to take my exhaust gases and use them to do what? To heat my steam in the boiler. Okay, because you know that for the gas turbine I reach much higher temperatures than for steam turbine. Okay, so after using the energy to rotate the turbine, I still have energy in the exhaust gases, and this energy can be used to drive a steam power cycle. So I can take it here, I can take it and use it at this level in the boiler. Okay, so it will be used to heat my steam, and in this case I will obtain a very high efficiency for the combined cycle, because using my gas turbine I don't only produce work at the level of the gas turbine, but also I am using the rejected heat to the atmosphere. Instead of losing it, I am using this heat to heat the steam in the steam cycle, and therefore I can end up with a very high efficiency. Because how to calculate the efficiency in this case? If I want to calculate the efficiency of the combined cycle, okay, first I am putting heat at which level? What is my input for heat? At which level is my heat input?
At the boiler.
Boiler.
At the combustion chamber here of the gas turbine. Okay, so here I am heating by combustion of fuel. I am heating at this level. This is Qn. Okay, now since I am not putting for the steam cycle, I'm just using the excess of heat rejected from the gas turbine, so I'm not putting any extra input here. Okay, so I just have Qn in the Brayton cycle. Okay, and now for my output, I have output at the gas turbine plus I have an output at the steam turbine. So my efficiency here will be the work of steam turbine plus the work of gas turbine over Qn. Okay, so in this way I will increase a lot of my efficiency, because for the same input of heat I am producing a higher work. Okay, because I'm producing work not only in the gas turbine but also in the steam turbine for the same input of heat. Okay.
Do we need to keep around the pump and the compressor powers? No, the work in.
Can you repeat your question, please?
Do we take into account the pump and the compressor in?
No, look, the compressor, if you want here in general, yes, you can consider, you mean that we are putting work in the compressor, but look, in general, the compressor, when we say W turbine, okay, we mean W net, because always, okay, we'll subtract from when we, if you want, we can write here minus W pump. Okay, of course, minus W pump 1 and minus W pump 2. But in general, the work at the pump level, it's very small. It's very small that it can be neglected compared to the work in the turbine. So to be very accurate, yes, we should subtract W pump 1 and W pump 2, or we can just say W net. Okay, we can say W net,
Okay.
W net of cycle 1 plus W net of cycle 2. Sometimes they neglect W pump because it's very small compared to W turbine. Okay.
Okay, thank you.
Any other question? Okay. So this is the material of the course. I just look, I will not give you complex calculations. So for example, I will not give you several cycles and at the same time and calculate all properties. No, but I want you to understand the concept, how we can improve the efficiency. If we increase the pressure, let's say, as we have seen before for the Rankine cycle, what will be the effect? If we have reheating, what will be the effect? Okay. Now for calculation, I will just test concepts. So like the problems I am giving you. Okay. So now we will continue the problems together of chapter 3, and I will open a new session. Okay.